This is an AI-generated documentary reconstruction for educational purposes. These are not real historical recordings. We are reconstructing the 1906 San Francisco earthquake and the engineering chain reaction that turned ground failure into a firestorm. The central paradox of this disaster sounds almost impossible. The city was surrounded by water, yet it burned because water was missing. The answer was not in the bay. It was beneath the streets. When the hydrants were opened, the system had already failed. More than 300 water main breaks turned the network into a sieve, and pressure vanished exactly where it was needed most. Dynamite was meant to stop the fire by creating firebreaks. But without precise calculation, explosions often turned buildings into burning debris and helped the fire move farther. To understand why San Francisco burned, we must rewind time to 5:12 a.m. on April 18, 1906. Before the shock, the city looked stable. Rails were straight, pipes were hidden underground, and brick facades stood upright, but the entire system depended on a fragile balance of soil, water, gas, and fire. At about 5:12 a.m., the main shock began. Within seconds, the San Andreas Fault transferred its energy into the city's soil, buildings, and underground utilities. The fault did not lift the city like an elevator. It moved sideways. In some zones, horizontal displacement reached several meters, and in this reconstruction we visualize a high-end estimate of up to 6 to 8 meters. The strong shaking lasted roughly 45 to 60 seconds. For brick, cast iron, timber, and old masonry, that was not a moment. It was an engineering eternity. Liquefaction happens when water-saturated soil loses strength under vibration. For a short time, the ground stops acting like a reliable foundation and behaves like a moving liquid mass. The rails became a visible indicator of invisible ground displacement. The metal revealed the direction of forces that had moved beneath the city. The destruction of City Hall became a symbol of the vulnerability of old monumental architecture. Visual mass did not save a structure that could not resist lateral shaking. The danger did not come only from large buildings. Chimneys, cornices, facades, and timber structures became sources of new damage and future fire. After the earthquake, every damaged system became part of one chain. Wires created sparks, gas supplied fuel, and the broken water system removed the city's defense. When the shaking stopped, the disaster did not end. It only changed form, from seismic failure to engineering failure. Cast iron performs well under certain loads, but it does not tolerate sudden bending and displacement. When the ground moved sideways, the pipe could not move with it. The water did not disappear magically. It escaped into the ground through hundreds of breaks. For the fire system, that meant one thing: pressure fell faster than the fire spread. Gas lines made fire not accidental but likely. After the shock, invisible clouds of fuel appeared beneath damaged blocks. This was not one accident, it was a connected failure system. Water moved downward, gas moved upward, and sparks searched for fuel. Pressure is the invisible armor of a city. When it falls towards zero, even a large water supply becomes useless to a district that water can no longer reach. More than 300 main breaks and many damaged service connections turned the city network into an open wound. The fire was visible above ground, but its cause was unfolding beneath the pavement. From the outside, it looked like a firefighting problem. Inside the system, it was a loss of hydraulic continuity. Water could not travel from the source to the fire zone. After the earthquake, an ordinary kitchen became a dangerous machine. A damaged pipe, a cracked chimney, and leaking gas could start a fire without any dramatic trigger. Pipe damage worsened ground damage. Leaks washed support from beneath streets, and already damaged infrastructure began destroying itself. By the morning of April 18, the fire was no longer a single blaze. It was a network of ignition points fed by gas, wind, wooden construction, and the absence of pressurized water. Firefighting tactics depended on one simple condition: water had to be inside the pipe. When that condition failed, even correct actions produced the wrong result. One of the known fires became known as the ham and eggs fire. Its importance is not the domestic detail but the mechanism. A damaged kitchen became the ignition point for a large fire district. In wooden construction, fire rarely moves only across facades. It travels through attics, eaves, and interior voids, carrying heat where water can no longer reach. The main lesson of the disaster is simple. Having water near a city is not the same as having water inside the system. Infrastructure matters more than geography. The US Army under General Funston took part in creating firebreak lines. The idea was logical: remove fuel ahead of the fire. But execution became the decisive factor. Dynamite can stop fire only when it is precisely calculated. If the blast scatters burning materials, the firebreak becomes a new mechanism of spread. When separate ignition points merge, the fire is no longer the sum of small fires. It creates its own draft, its own wind, and its own speed. A fire vortex forms when hot air rises rapidly and cooler air is drawn in below. The city street grid becomes a system of air channels. Extreme heat changed material behavior, glass cracked, metal lost stiffness, and masonry failed under thermal expansion and impact. The disaster exposed the difference between mass and resilience. A heavy building can look strong, but without proper structural design, it loses against lateral forces and fire. The fire did not move randomly. It followed fuel, wind, building density, and the absence of water resistance. This was physics, not mystery. Warehouses, wooden crates, and dense commercial blocks became additional fuel. The city's economy itself became material for the fire. The transport network also became a victim of displacement. Twisted rails showed that the city had lost not only buildings, but also the ability to move and supply itself. By this point, fire had become the main destroyer. The earthquake delivered the first strike, but the fire consumed space block by block. The chain was clear: fault slip, liquefaction, pipe ruptures, pressure loss, gas leaks, sparks, dynamite mistakes, and a firestorm. After 3 days, the city had become a grey engineering diagram. Where streets once stood, foundations, pipes, rails, and answers remained. These rails and pipes became physical evidence. They showed where the ground flowed, where metal bent, and where the city system lost continuity. About 490 city blocks were destroyed by fire. That number shows the scale not only of the fire, but of a systemic urban failure. Damage was estimated at roughly $400 million in 1906 values. For a city of that era, this was not just a fire, it was a financial rupture. The ferry building became one of the major symbols of surviving engineering. Against the devastation, it showed that cities need not only beautiful facades, but calculated resilience. The main engineering lesson was simple: buildings must not only carry vertical weight, they must survive lateral acceleration, foundation deformation, and fire after the shock. After the disaster, the question changed: what happens if the normal network fails again? The answer became backup sources, cisterns, pumps, and independent fire water supply. Rebuilding was not simply construction again. It was an attempt to rewrite the rules: how to build, how to supply water, how to separate fire, and how to account for soil. San Francisco in 1906 teaches that a disaster is rarely one event. It is usually a cascade, where nature delivers the first strike and weak systems decide the scale of the consequences. The 1906 earthquake destroyed more than buildings. It destroyed the belief that a city can be understood by its facades. Real strength is hidden deeper, in the soil, the pipes, the frame, and the system's readiness to fail safely.